The most fundamental constant in all classical physics remains stubbornly elusive. Newton's gravitational constant, the number that describes how hard gravity pulls, has eluded precise measurement for over 225 years. Physicists have refined their experiments again and again. Different laboratories still arrive at different answers. Not by a little, by amounts that should be impossible according to our understanding of experimental error. In April 2026, a team at the National Institute of Standards and Technology published the results of a decade-long effort to measure this constant with unprecedented precision. The measurement deepened a mystery that now touches the foundation of how we understand the universe. The answer matters because everything depends on it, from calculating how planets orbit, to predicting the fate of stars, to understanding the very birth of the cosmos. And despite centuries of effort, we still don't quite have it right. Isaac Newton published his law of universal gravitation in 1687. Every object in the universe pulls on every other object. The force is proportional to their masses and inversely proportional to the square of the distance between them. The formula is elegant, simple even. F equals G times m1 times m2 divided by r squared. G is the gravitational constant. Newton never measured it. He didn't need to. His law described how gravity worked without requiring a specific numerical value for G. That came later, and it has come with unexpected difficulty. For more than a century after Newton, physicists could not isolate G. Scientists could measure gravity's effects with precision. How fast objects fell. How planets moved around the sun. But they couldn't extract G itself from the mathematics. It hid within the equations. In 1798, Henry Cavendish built an ingenious apparatus. He used two small lead spheres hanging from a torsion balance, larger masses fixed nearby. The tiny gravitational attraction between them caused the balance to twist microscopically. Cavendish measured the twist and calculated G from the result. His value stood as the most accurate measurement for decades. Then something unexpected happened. Subsequent measurements disagreed with Cavendish. More troubling, they disagreed with each other. Different teams using different experimental techniques arrived at different values. When physicists looked at a century of measurements, they expected the scatter to shrink as methods improved. It didn't. Modern experiments using sophisticated instruments still produced answers that didn't align. High-precision measurements now spanned a range that far exceeded what experimental error alone should produce. The numbers told the story clearly. Different high-precision experiments disagreed by approximately 1 part in 10,000. That is vastly, impossibly larger than routine uncertainty can explain. If scientists built identical instruments and used identical methods, they would expect disagreement on the order of 1 part in 100,000 or smaller. The observed scatter was 10 times too large. By the late 20th century, physicists faced an uncomfortable truth. They knew the gravitational constant less precisely than any other fundamental physical constant. Scientists had measured the strong nuclear force to far better accuracy. They had determined the weak nuclear force with greater precision. They had fixed the speed of light. They had measured the electron mass. They had calculated Planck's constant. They had pinned down the fine structure constant. Every other fundamental constant yielded to measurement more easily than gravity's did. The constant that Newton left behind, the constant that governs the most obvious force in everyday life, scientists could determine only to 3 significant figures. That limitation troubled the field deeply. Stefan Schlaminger at the National Institute of Standards and Technology decided to tackle the problem directly. In 2014, he and his colleagues began a decade-long project. The goal was to measure G with extreme care, accounting for sources of error that other experiments had missed or underestimated. They had to control for factors that might seem trivial: magnetic fields from nearby equipment, vibrations from traffic outside the laboratory, tiny variations in temperature, the mass distribution of their apparatus, every possible source of systematic error. In July 2024, Schlaminger and his team presented their findings at a physics conference in Colorado. The results were striking. In April 2026, they published the complete analysis in the journal Metrologia. Their measured value for the gravitational constant was 6.67387 times 10 to the negative 11 meters cubed per kilogram per second squared. This is a number of extraordinary precision. It is also notably lower than a competing measurement performed by the International Bureau of Weights and Measures in France. The NIST result is about 0.0235% lower than the French measurement. In absolute terms, that is a tiny difference, but in the context of fundamental physics, it might as well be enormous. Both teams used completely different experimental methods. Both employed extraordinary care and precision. They had every incentive to converge on the same answer if they were both measuring a true constant of nature. Instead, they diverged. They pointed in opposite directions, and no one fully understood why. The implications forced physicists to confront uncomfortable possibilities. One explanation was that one team made a hidden systematic error. Experimental physics is unforgiving. Despite every precaution, hidden biases can creep in undetected. A magnetic field acting in an unexpected direction. Vibrations from a source the team didn't anticipate. Temperature variations that weren't caught. A calibration error that survived all quality checks. A single overlooked source of bias could skew the results significantly. But that explanation grew harder to accept when multiple teams using different methods all disagreed. If only one team measured G differently, a hidden error in that lab would be the obvious culprit. When multiple independent teams obtained different answers despite their best efforts, the possibility of coincidental errors became less compelling. Something more systematic might be wrong. This led to a darker possibility. Perhaps different measurement techniques genuinely measured different things. Perhaps the gravitational constant was not truly constant. Perhaps G varied subtly with location, or with time, or with some condition that current theory didn't account for. Or perhaps G depended on the mass of the objects involved, or the distance scale being probed in ways that Newton's simple law never predicted. The third possibility ventured into deeper physics. Einstein showed that gravity is not a force at all, but a consequence of space and time curving around mass. General relativity makes no explicit use of Newton's gravitational constant, yet the constant bridges classical gravity and quantum mechanics. Physicists have never unified these two domains. Gravity remains antagonistic to quantum theory. This unresolved discrepancy in measuring G might be a signal. It could hint that something fundamental is missing from our understanding where classical and quantum worlds meet. The NIST team did not resolve the mystery. Their measurement added another precise value to a growing collection of contradictory answers. It sharpened the problem without solving it. Physicists must now choose between uncomfortable alternatives, assume that multiple teams made hidden mistakes no one has discovered, or entertain the possibility that our theories are incomplete in ways we haven't yet recognized. The gravitational constant appears in every calculation involving gravity. Astronauts use it. Astronomers use it. Physicists studying the cosmos use it. How well we know G determines the precision of every such calculation. If G is truly uncertain by 1 part in 10,000, it means gravity itself is less well understood than we believed. Newton's law still works. Satellites still orbit. Planets still move. But the mystery of what G truly is remains unresolved.